at Invisibles18 workshop. I'm going to tell you about solving the strong CP problem with model building using exotic color groups. And the sort of main example I'm going to use is a model called the Color Unified Dynamical Axion, which is work I did in collaboration with Mary Kay Gaillard, Failing Gavela, Rocio Del Rey, and Pablo Quiles. And you can find it on the archive if you're interested. Okay, so as you've sort of heard many times by now, QCD has a CP violating term in its Lagrangian with a theta coupling. Experimental measurements found well, the physical theta to be very, very small. So this could be a fine-tuning problem in the standard model. And one of the most famous ways to solve the problem is by introducing a Ullmann-Paget-Quinn symmetry, of which the axion is the Goldstone boson, and then when it's broken by anomalous contributions from GG dual, you get an axion mass and this is the Goldstone boson. And as we've seen in the last talk, the most like typical axion models live in this line parameter space, where the x-axis is the axion mass and the y-axis is the axion coupling, or 1 over the dynamical scale of the axion. And experiments are probing this whole space. And like Pratik, I'm also curious and looking for models where we can find an axion outside of this invisible axion parameter line and see if we can find axions that solve the strong CP problem in QCD, maybe somewhere else in the parameter space. I'm going to show this plot again where we go to higher masses. And here you can see the collider constraints on the invisible axion region. And so yeah, if you could go this way, maybe you could see a collider reciprocal axion. So another way to solve the strong CP problem is with massless quarks. Under a chiral rotation, here's just QCD with massive quarks and GG dual. If you do a chiral rotation on the quark fields, that's a field redefinition, which shows up in the anomaly, and you get a shift in the theta parameter. So if this is 0, you can see that doing this chiral rotation, just redefining the fields, just gives you a free shift in theta. So you can freely rotate theta to 0, and you wouldn't expect to see a strong CP problem because theta is no longer visible. The simplest way to do this is to say, well, maybe the standard model up quark is massless. But this has been disfavored by lattice data. But this whole thing would still work if you had an exotic massless up quark. And if you did that, you'd have to hide it somehow. All right, so hopefully I've motivated 2 reasons why it might be worth it to think about extending the color sector of the standard model, or the theta of the strong sector. But I mean like QCD, and then maybe other confining gauge groups. So one reason is that additional color interactions could alter this MA-FA relationship. So in the standard model, it looks like M pi, F pi, but if you had some other interactions, very generally, you might get contributions that go like the confining scale of those new gauge groups. Another reason to extend the strong sector is if you do solve the strong CP problem with a massless quark. Obviously, we haven't seen these massless quarks, but if they're charged under some new force, and that new force confines, like QCD, at some high scale, then these massless quarks very generally would form bound states around the size of the new confinement scale. So I think these are 2 reasons to maybe start thinking about more complicated solutions to the strong CP problem and to and extending QCD. And I'm mostly going to talk about this type of solution because in the end it gives dynamics that are kind of similar to what show up here. So sort of the prototypical example of this is AxiColor. AxiColor is a model that was written a long time ago by Choi and Kim. And they really just did the most simple idea, right? So you have a massless quark charged under QCD and charged under some exotic color group. And this exotic color group, just for whatever reason, confines at some high scale, much larger than QCD. When this other gauge group confines, the massless quark forms bound states at lambda tilde. The problem is, though, if you introduce a new non-abelian gauge group, you introduce a new theta angle, or as in the last talk, the idea that adding these new interactions might shift around your solution to the strong CP problem. And the solution that Kim did is to absorb theta tilde with a new massless quark. So they added a second quark that's only charged for this group. So one field-directed redefinition can absorb this theta angle. A second field-directed redefinition can absorb this theta angle. And you solve the strong CP problem. When SU tilde confines, you get, there's a SU4, there's red, green, blue, 4. So SU4 left cross SU4 right chiral symmetry breaking gives you these pseudo-Goldstone bosons, and you end up with something that's a pseudo-scalar singlet coupled to GG dual, which is formed out of these massless quarks, which becomes the dynamical axion. And in this model, they didn't really get outside the invisible axion region. You end up with an axion decay constant near this high confinement scale, and this guy doesn't have enough sources of mass, so it becomes light, and this is just a UV completion for an invisible axion model. And I showed you this example because this is sort of the problem you always run into. You can always kind of play this game, forever. So you add an additional color group to contribute to the axion mass. The new group has a new theta angle. So you introduce some new mechanism, a new massless quark or a new axion to absorb the theta angle, and you get stuck with a light axion again. And you can kind of get stuck in this loop. So here I showed with like massless quarks going on forever, or this is very, very, very heuristic because there should be constants here. But if you have some new scale here, it might give mass to this new scale. Some new scale here gives mass to this. But then lambda QCD is giving mass to the eta prime of QCD and the axion. The eta prime gets most of the mass, and the axion is the aggregate that's left over to mix with the pions. So you're always sort of stuck. So one way you can avoid getting stuck is by finding a way to relate theta angles between two groups. Houtz did this, where he said, all right, I have the standard model, and then I have just a complete copy of it, and they're related by a Z2 symmetry. So if you look at just QCD, you have QCD standard model, then some extra QCD. Then what he says is, if these guys are related by some symmetry at high scales, I'm going to set up one Higgs set to be much larger than the other, so all the matter in the mirror world is very heavy. And then you get that the QCD in the mirror world confines at a much higher scale than lambda QCD. And the bound states that form here are composed of massless quarks, and they lived at lambda prime QCD. So he was able to achieve it by only needing one massless quark and not needing to add a second because the symmetry related the two. So thinking along those lines, instead of using a discrete symmetry, another way to do this could be unification. So here I showed, this is not what I'm going to talk about, but I showed kind of the prototypical example of unification, where the standard model gauge groups may be unified at some high scale. Here I sketched sort of our idea of unification of what we want, which is that maybe there's QCD and there's some SU3 tilde, and maybe at some high scale they come together and unify into a unified color group. And we're not the first people to think of this. Gergetta did a very similar paper with unification and axion, and Ruberkoff did something similar with dynamic theories. And so what we did in our paper is that we did this with a massless quark. QCD in our paper lives inside some larger color group, which then breaks to QCD and SU3 tilde at some high scale. And this massless quark absorbs the theta angle of the unified group. And then the idea is that this guy, if we can do it right, which is non-trivial, this guy can confine at some higher scale, and we get bound states near the TED, and we get heavy axions. And the idea, again, to remind you, is to really get out of the MA-FA relationship. So hopefully this model gives a dynamical axion that has some different relationship than the typical invisible QCD axions. To get into the details, we had some SU6 that breaks with some lambda cut instead of gut, it's cut because color unification. SU6 breaks to QCD, SU3 tilde, and U1. In SU6, you can put a massless quark on the 20 representation of SU6, and then for completion, it's just a singlet of SU left and not hypercharged. And just to let you know that these guys are not unifying with anything else. And then when this breaks below the unification scale, we end up with massless quarks that have this pattern under QCD and SU3 tilde. And then the other really important thing, is if you're going to unify everything, you need to put the standard model quarks in gauge invariant, or in some representation of SE6 so that they can form gauge invariant transsingular Lagrangian. So we put them in 6 multiplets of SE6. So now we have our standard model quarks just in fundamental representations. One of them is charged under SE2 left, just like the standard model. And then we have a massless quark living here. Then we break unification. This step here is the standard model matter constant. These are sort of like if every quark has 3 partners to get 1, 2, 3, 4, 5, 6. These are the unification partners living here. And then our massless quarks end up like this. Where this guy is the one that's going to absorb the theta angles, and this is like a very, very light neutrino singlet under all the gauge groups. So the main goal here is to provide a mechanism for these fields to form a mass. And this is very important, right? Because if we have QCD and some other group unify, without there being any difference between them, they would run together and just confine at the same scale, right? What governs the RG flow is the matter content of the theory. So it's very important that these guys get integrated out at a higher scale so that we can alter the RG flow of this other group. Also, we haven't seen these quarks, so they should be massive. So it's also important. And this, if you're interested, we can talk after. I don't have a lot of time, but this is highly non-trivial because of this guy right here is charged under SE2 left, so it's hard to get rid of him without messing up electron symmetry breaking. All right, so how we did it here was our original color breaking pattern. So we added an SE3 prime group, and matter in the SE3 prime sector can form mass terms of the unification partners. And then once those mass terms are formed, then both can be removed from the low energy spectrum. It was looking really complicated, but it gets a little better. So then these guys come together and form some diagonal gauge group. So the low energy gauge group here looks very, very similar to the low energy gauge group here. So we have a similar gauge structure, and our low energy sector just has the standard model quarks and the massless quarks, which is what we wanted. But we've kind of introduced a major complication here. So this guy, we added another non-abelian gauge group. So it has its own strong CP problem, so we need to add another massless quark to absorb the theta prime angle. So that's this bit of model building resulted directly from trying to decouple the SE6 partner fields. All right, so this is what our theory looks like. At high energies, we have the SE6. This is like the color unified group. Then here's our SE3 prime gauge coupling, which is mostly here just to give matter concept that can form partners with the standard model fields SE6 partners. So here at the scale, this guy partially breaks with part of this, and then this breaks to 2 groups. One is QCD, and one is SE3 diagonal. And then we were managed to find some parameter space such that this confines at a nice scale higher than QCD. So that all worked out nicely for what we wanted. So what happens when SE3 diagonal confines? Again, we get this U4 left cross U4 right chiral symmetry breaking, resulting in 16 pseudo-Goldstone bosons. This is looking a lot like the Schwing-Kim example. So the 8 splits and the pions that are charged with QCD actually get masses from gluon interactions that pushes them up to the cutoff scale. These are quadratically divergent diagrams. And then the eta prime gets its mass from anomalies. And our low energy effective Lagrangian, we get a contribution from the confinement of the diagonal and a contribution from QCD. And it looks like I'm back at the beginning. We have 2 masses for 3 eta prime pseudoscalars if you include the eta prime of QCD. And we're stuck with one of these being a light invisible axion. Except there is other sources of axion masses, as was pointed out just in the previous talk. So typically at high scales, QCD is very small. But that's not always true, depending on what you do with the RG flow. So if new physics alters the RG flow, large couplings at high scale can induce new instanton corrections to the axion mass, just like what was just shown. So for one example is Flynn and Randall did some computations of this, where they throw a bunch of new matter content in here to QCD, so much so that they reverse the RG flow of QCD. It runs to some higher scale, and then instanton effects between here and here contribute to the axion potential. And then very recently, Pratik Agrawal and Kyle Howe did the strong CP problem, which is the talk you just heard. And the idea here, which I'll just summarize again, is that there's this S23 cross, S23 cross, as many as you like, breaks to QCD. If this is alpha QCD, this breaking pattern follows this relationship. You can imagine taking one of these gauge couplings and making it very, very large, and it would have a very, very small effect on QCD in the end, right? Where this relationship holds at the breaking scale. So you can see the potential to get large gauge couplings in the UV from the diagonal breaking pattern, and then instanton effects would be important. And we have this nice, not too strong, still perturbative, but decently strong H coupling sitting up here at the high energy physics, which can then contribute to the axion potential. So here's a new source of axion mass that was pointed out by other people. You've now seen this diagram a few times, so you should totally be comfortable with it, right? You do this approximation, you can do this instanton calculation, and you get this new source of axion mass for the eta formed out of the chi massless quarks. Where these are the typical contributions from the confinement, QCD confinement, and then here's the new small-sized instanton effects that come from stronger gauge couplings in the high energy theory. And so when we did this and calculated our axion masses, here's what we got. So on the x-axis, we have the alpha prime coupling evaluated at the unification scale, and on the y-axis we have the mass for the axions. There's a lot of lines, but I'll explain what they are. So the two rainbows are the two mass eigenstates of the etas, right? Because the etas mix and they have two eigenstates. And then within, so let's just take one set. This line is for one cut scale. So this is 10 to the 18th. So this is maybe a bit, this is like a point being cut scale, which is realistic. But then you can see what happens. Here's 10 to the 17th cut, 10 to the 16th, GeV, 10 to the 15th, GeV, 10 to the 14th. So these are different cut scales. And you can see how the axion mass changes as this alpha prime value changes. And then they go from solid line to dotted line. Because if you lower the cut scale too much, maybe the best way to think of it is this way. If you lower the cut scale too much, eventually the diagonal confinement scale is low enough that you start seeing these exotic ions and they be ruled out. So the dotted lines are just like ruled out or not promising models. And the general behavior is that one of these mass eigenstates is quite large and it falls off when this instanton effect turns off, which is what we'd expect. And then also another thing is that these instantons these axions are just really heavy, like way too heavy. So they're not even, it's even difficult to see them at colliders. So this source of axion mass was too good at giving their axion mass in our model. And then to remind you, so now we're having mass axions that are like living out here, so they're totally unconstrained, and they're definitely off of this invisible axion line, which is nice. If they are too heavy to see at the LHD, we still have some colliders we know to do from our model, and this came from the QCD colored pions, like for example the octet pions, so they can be pair produced and they can anomalously decay. And the colored octet pions, you could reinterpret bounds on gluons, which is a proposed particle in supersymmetry. And these bounds from gluons, you can turn that into a bound. The bound on the masses of the pions can be turned on into a bound on the confinement scale, which gives us a bound of about 3 TeV for the confinement scale, and in all my plots, that was the confinement scale, which was sort of something I was predicting. All right, so the summary for what we did is that we were able to solve the strong CP problem using massless quarks and unification, which is sort of a different twist on how it's been done. And then the nice thing is that the unification scale and the confinement scale are very naturally separated by the RG flow. But the not so nice thing is that decoupling the unification partner fields was non-trivial and actually required significant additional model building. And then one of the cool things is we were able to use the small-sized instanton mechanism that was pointed out by others that provided an extra source of mass for our axions. And in our model, the promising collider system was from the exotic pions that came from the confinement of this group. And I think, so for some conclusions, extra color groups can provide a window to richer phenomenology. So you can see visible axions, where MA, FA can get additional contributions from intrinsic scales of other gauge groups. It makes the massless quark solution still viable. Maybe not the massless up quark, but maybe massless exotic quarks could be hidden by these exotic color groups. Symmetries are usually needed to simplify the CP violating phases. So you might need, if you're going to add extra color groups, it might be good to relate them to one another. But that's not the only way, because there's also non-perturbative effects at high scales can provide extra sources for axion masses. So there's a lot of really fun model building going on in axion physics right now, I think. Thank you.
Thank you. It was very clear talk in a very short time. So, please, I have a question. So you're doing all of this model building trouble basically because you want to evade the second CP phase in this new. So I don't understand what's actually the problem of having. Can we not live with the CP phase in this new gauge sector?
So you could if it was completely sequestered, but so you can see that this group, or well, this isn't a great representation. Okay, let's go back. So this group here, it is going to provide mass fields to guys charged under here, has interactions with here. These interactions are happening at a very high scale, so they're very suppressed, but the bounds on the ZP violating phase are also very strong. So yeah, you could create a secret hidden value that doesn't touch the standard model at all, and then you could violate CP. But if you're going to use it to do anything you want, it can communicate the CP violation to the standard model. If it talks to the standard model, like how rotations in one field can be back for rotations in the other sector, and then rotated to the theta angle. So, yeah. Does that answer your question?
Yes, thank you.
Just a couple of questions.
Mm-hmm.
Thank you very much for the talk first. Second is more related on the fact that the scale is one that cut that you have seems very high.
Yes.
So for example, if you think about the paper by Rodrigo and Alfredo a few months ago about gravitational effects, if I remember correctly, it was an exponential with the ratio of this new scale and the Planck scale. This seems to be a trouble maybe. And second of all, the fact that you have these very heavy objects around in cosmology is not a problem?
So it can be a problem in cosmology. We're thinking about addressing that now. For what we did so far, you can imagine low-scale inflation would inflate a lot of these problems away, but then we wouldn't have any cool dark matter candidates. So right now we're thinking about like the cosmological implications. Yeah. Addressing your first question, maybe we can talk about it afterwards. I remember reading about this, but I don't quite remember the details of the talk.
Okay.
Yeah.
Thank you.
Yeah, oh wait, maybe Galen has a good answer for you.
For the axiom, the non-perturbative effects you are thinking about the gravitational non-perturbative of the axiom, here the axiom scale is at the TV. The other scale does not have a Pechey-Quinn symmetry. So for what you are thinking, even without the vector of Rodrigo and the others, that on the contrary would allow even higher scales if it applied. But forget the last paper. Suppose you are worried about the gravitational effects, you have them when you have a scale close to Planck as a scale of spontaneous symmetry breaking. Here, the Pechey-Quinn scale is a lambda diagonal, which is a few TeV. Okay?
Yes.
So, because you work for it, you know very well.
I appreciate it, yes. It's true. This is one of the very nice features of this model, is that like the dynamical scale can be as low as here, and the undesirable, or like, you know, the extra model building effects can be as high as here, and these scales are naturally separated by the RG flow, which is nice. So yeah, like the GG dual effects are coming in here, which is much lower than any of that.
Thank you very much.
You're welcome. Thank you, Bailey.
Questions? Yeah, just you.
So first, thanks for the talk. My question is related to what was discussed now. So on slide scale lambda. And my question would be that if the scale lambda is smaller than the axial decay constant Fa, is this a scenario where this is possible, or does the scale always have to be bigger than Fa?
This is something we're talking about now. Like particularly our axions are composite states, so above planes of diagonal, then thinking of them as bound states isn't quite the right mechanism. So instead you could think about the free chi as being massive, and then it would be more like a massive upwork solution to the strong CP problem, because you would get an apparent mass from instanton effects, but it would still be able to rotate away the strong CP problem. If that were true, then you wouldn't have it hanging around in confinement. You'd only have the other eta prime made of the psi, and then you wouldn't have everything would work out just with a slightly different interpretation. So yeah, we're thinking about that now. I didn't put it in the slides because we haven't totally worked out all the details. Once we have that, I'll let you know. But you could very easily look at it as this guy breaking apart, and then the instantons giving the chi a mass, and then the chi wouldn't be sitting around, so the instantons wouldn't be needed, in that position. So,
Okay, thanks a lot.
Yeah.
You just mentioned in passing in one of your replies that you could address dark matter in the setup. So can these particles ever be stable enough for that purpose?
Maybe we should wait for more information. We're still working on this.
It is become very interesting, and we have solved this with Julius Wilma, but we have not written it, so
to be continued.
But what is interesting is that these models apparently also lead you naturally to another way of looking at that matter. So that, because what she was saying, in the paper published, we said, okay, at the moment let's consider the inflation scale very low, and we get rid of all problems with instead of cosmology. But we are throwing, how do you say, the baby with the water or something like that. So we realized that, in fact, this is interesting. We hope to write it soon. Comprehensive.
Yeah, so it wouldn't be the pions, it would be other bound states made of the exotic gauge group. The pions decay anomalously, if that was your question. But there are variant states, so we're still working out the details.
Some of your new fermions have an SU2 or a U1 half charge. So is your most minimal model automatically anomaly free, or do you have to add in extra fermion content?
We checked the anomalies and we were able to make them all cancel, but we do have to add in extra fermion content to give partners to these fields, absolutely. Here everything is anomaly free. So the SU2 left guy is okay if its main dominant mass contribution doesn't come from the Higgs, which is the case in what we did. It's bad. This guy is really bad if it's if it's still around when the diagonal confines, because then that triggers electric symmetry breaking. So this guy really needs to be removed by something else. But yeah, we did add extra fields in the prime sector that then get removed through the mass terms. Yeah, and all the anomalies cancel.
A very down-to-earth question. You had a lot of matter content,
yes.
And at some point, exactly in this table, you mentioned that you were adding some very light states.
So these guys are massless now, right? Is this what you mean? And you can imagine maybe them getting a mass, but we didn't look into this too much. But whatever they are, their couplings they're completely not coupled with standard models. So all their couplings are suppressed by lambda cut. So you need to invent a mechanism for it. But yeah, we just sort of didn't examine their too much.
And related to that,
yes.
in the nice rainbow plot that you had, you say that basically you are beyond collider reach, but this lilac line, the one diving, it looks like it's 15V.
Here?
Yes.
Yeah, so right, we're in collider reach in this tiny parameter space, but it's a bit unrealistic because it's a Planckian unification scale. But it's more just to give you a sense of the trend of this line, if you like. So maybe a better sky, even this I think is so close to the Planck scale, maybe unrealistic. I'm more comfortable with these lines. And here we're getting into 10 TeV. So yeah, we're maybe just at the edge of collider reach. But most of the parameter space is outside. Yeah.
Thank you.
So if I'm maybe just to mention, she didn't describe in the same paper, we have a second model where one of the axioms can come down to the GEV, in fact. So, a more overall comment I think this is too complicated in the sense that the moment we start putting the SU3 prime, the thing grows complicated. I am convinced that you can do this much simpler. I mean, all that extra paraphernalia is just 2 bit masses to 3 elements, right? And we think we may arrive to do it much simpler. But so the basic idea, this is just the first model using color verification and mass response, and it works. Then to find some matters we want, we have to push them up, and I think that it should be done. It should be possible to do it simpler. But this is a proof of concept that you can do it. And also that, as I was saying, you do a small variation, and one of the actions becomes near the GV. You don't need to have the two very high.
So in principle, you could verify it via some discovery.
Anyway, you can verify because she said, the collider, there is this characteristic of the collider, a prediction of colored meson, octets of mesons. So that it's like that's going to remain. The center remains in sterile neutrino, but it couples to mesons, so you don't know what to do with it. You say this there, decouple very, very early. So that seems also unavoidable. No? Beyond the details of how we got rid of some masses.
Yes, I think the moral of the story is this is still very much in the model building phase, and maybe if we find something we like more, we'll do deeper, but yeah.
Okay, let's have.